Almost everyone has heard of Einstein's special theory of relativity. It was truly groundbreaking. But it doesn't have to be complicated or hard to understand. In fact, I bet we could formulate it ourselves. The theory had two postulates, or parts. The first one said simply that the laws of physics are the same in any inertial reference frame. A reference frame is just what a person considers to be at rest. I say considers because you could also consider it to be in motion relative to something else in the universe. Wow, it sounds like we're developing a theory of relativity. So Einstein said that the laws of physics are identical in any inertial reference frame, meaning one that isn't speeding up or slowing down. But why does the speed have to be constant? Well, that's easy to prove. Just sit in a chair, grab a bowl of popcorn, place it in front of you, sit back, and watch how the laws of physics behave. Nothing's happening. Now let's do the same thing in a car with the windows blacked out. What if the driver decides to change the speed of the car drastically by stopping all of a sudden? All of a sudden, the laws of physics seem to act a bit differently. But if the car travels at a nice constant speed, then the exact same thing happens as when I was just sitting on the Earth. Nothing. In both the reference frame of the Earth and the car, the popcorn doesn't move. Both the Earth and car were moving at different speeds, but as far as I could tell, the laws of physics acted exactly the same. Thus, we can conclude the same thing would have happened in any frame of reference that was also moving at a constant speed, and none of them would have been any less valid than any of the others. So there you have it. We just proved the first postulate. The second postulate says that light travels at a constant speed in a vacuum regardless of the speed of the source of the light. Now, how did Einstein come up with this? Back in the 1800s, people just realized that light travels as a wave. Another kind of wave they were familiar with was sound. Now, sound waves like these require a medium to travel through, some kind of matter. So people concluded that light waves must also need a medium, and they called it the ether. Now, how do you prove or disprove the existence of a hypothetical medium? Well, if you're Michelson and Morley, you use an interferometer. This device measures differences in the speed of light that would occur if there was such thing as an ether. Light was split along two perpendicular arms, reflected back to the center, and caused to converge in an eyepiece, and the interference of the waves would create a pattern. If the light traveled at different speeds down each arm, it would reach the eyepiece at different times and create a different interference pattern, one shifted over by, say, this much. If there was an ether, the Earth would pass through it on its orbit around the sun. On Earth, this would make it seem like the ether was moving. If light required the ether to travel, you can see from this diagram that the light traveling against the motion of the ether would have a slower speed than the light traveling perpendicular to the ether. Thus, the interference pattern would be shifted over. But when this experiment was actually done, the interference pattern wasn't shifted over, indicating that nothing was causing the light to move slower. Light, therefore, didn't need a medium. In any given reference frame, light wouldn't go slower because the thing it was traveling through had its own motion, because the thing it was traveling through was empty space, which doesn't have any motion. It just is. And so the speed of electromagnetic waves traveling through empty space also just is. There you have it. One of Einstein's greatest achievements, and we came up with it ourselves in a couple of minutes. Makes it seem kind of simple, doesn't it? So, what's so revolutionary about this theory? Well, one of the strangest phenomena that special relativity predicts is something called time dilation. You've probably heard this somewhere before. If someone were to leave the reference frame of the Earth and enter a reference frame moving very, very fast relative to Earth, then that person would return after what Earthlings considered to be 30 years, while the space traveler would only have felt 1 year go by. Using special relativity, we can answer the question, why does someone who travels very fast compared to the Earth experience time more slowly than people who stay on Earth? It's all based on the equation speed equals distance over time. When we use this equation to describe light, the speed of light is constant as long as you are measuring it from a reference frame moving at a constant velocity, such as Earth. The distance in this equation has to be the distance traveled by light, but that doesn't mean we can't use it to describe any matter in the universe. All the chemical processes that cause matter to change and the human body to think, to breathe, and age happen on a cellular level, a molecular level, an atomic level, and ultimately a quantum level, where everything is the result of forces carried out by photons, gravitons, and other fundamental particles which move at the speed of light. So, for any bodily activity to occur on Earth, the photons in your body need to travel a certain, very tiny distance, and since the speed of light is 670 million miles per hour, this distance is traveled, and the activity happens, in an extremely short amount of time. Think of a photon like a car traveling at 120 miles per hour just to get next door. It's going to take a very short amount of time. But when your body moves really, really, really fast compared to Earth, much closer to the speed of light, then your photons have to travel a much larger distance for those same bodily activities to occur. Since the speed of the photons and fundamental particles is constant, but they need to cover a much larger distance, they will have to do it in a much longer time. So your car is still moving 120 miles per hour, but it's going to take a lot longer to drive from New York to California than it is to drive next door. Since the same bodily change that happens on Earth takes much longer to occur when you are moving so fast relative to Earth, we say that time slows down for you relative to people on Earth. But you wouldn't notice a difference because your perception and everything traveling with you on the spaceship also rely on the behavior of light-speed particles and would have to slow down just as much as your body's aging process. So, the relativity of time is a natural conclusion if you just combine the speed equation with the fact that light travels with a constant speed. It just isn't a natural conclusion from our experience on Earth, where currently there aren't a whole lot of near light speed travel options available. But one day they might be, and when that day comes, it'll be thanks to Einstein's incredible understanding of how the universe works, despite never taking a step off the Earth, that we'll know exactly what to expect.